Right, this is 7.6 tree diagrams. I'll show you what those are in a bit, but let's just recall this die. There are 6 different sides, right? And they each have their own number. And it's just as likely that you would roll a 3 as it is that you'd roll a 1 because there's the same amount of sides that have that number, right? There's one side that has a 3, there's one side that has a 1, one side has a 4. Those would be equally likely. They'd have the same percentage likelihood of being rolled. You'll also recall, with coins, there's 2 sides, right? There's a heads or there's a tails. You flip, oh, it's a tails. But each action, there are different outcomes and they're equally likely. That's why, they use coins for doing this, for flipping at the start of a game or something like that, so that it's fair because it's either this or that. It's an option between the 2 sides. Side note, last year I had a student who flipped a coin and I saw it land on its side. That does not happen very often. The likelihood of that happening is almost 0, but it is possible. However, it's so unlikely that rounding the numbers, it would still be a 0 and each side would be 50% and 50%. Now, tree diagrams come in because sometimes an experiment will have more than one action. For example, what if I have 2 coins and I'm going to flip them? What are the chances that they'd both be heads? What are the chances that one would be heads and one would be tails? And what would the chances be of them both being tails? There'd be 2 actions. There'd be one coin that's flipped, off screen, and there's another one that would be flipped, okay? So there'd be 2 different actions. So let's look at this. Tree diagrams are a great way to organize these. Flipping coins is an example of what's called an independent event. Independent events are where one result, so what this coin would flip, for example, doesn't impact what the other one flips. If I flip a heads on this, that doesn't change what is possible for this coin over here. Both are going to have their same possibility no matter how many of these other events there are. They do not depend on each other. They are independent of each other. A tree diagram is a great way to organize independent events. So how you do a tree diagram is you organize it so that each event gets its own column working its way across or row working down. I prefer the columns. I find it looks a little neater. Now, looking at your first coin, if you're going to flip 2 coins, 2 independent events, try to figure out what's going to happen. What are the options for this coin? It could be heads. So let's use H for heads. Right? Or it could be, flip it over, tails, right? There are 2 different options. Now from that, what are the options that this other coin could be? Well, it could be heads or it could be tails, right? There's 2 different options. Now looking at this, if the first coin is flipped heads, its 2 options that it could be for the second coin are still heads or tails, right? And if the first coin was tails, the options here for the second coin are still, they're going to be heads or tails. So then we need to summarize the outcomes. The first coin could be heads, and the second coin heads again. So in that case, there would be heads and then heads, right? That would be the outcome. Both would be heads. So there's this one time here that both would be heads. Then our next one moving along, our next line would be heads and then tails. It'd be heads and then tails. So there's one of these here that would be heads and then tails. Moving our way down to our 4th line, tails and then heads. And then finally, tails, then tails. There's 4 different outcomes that could happen. Both heads, heads, tails, tails, heads, and both tails. I have a side note here. When there are multiple identical independent events, the total number of outcomes will equal the number of independent events times the number of independent events. So looking here, how many outcomes did we have? We had 1, 2, 3, 4. Which is equal to the number of events. There's 2 events happening, right? The 2 events happening times the number of independent events. the number of outcomes for independent events. So right here, how many outcomes were there for an independent event? There were 2 outcomes, right? Here, there were 2 outcomes for independent events. So you take that 2 and you multiply it by the 2 times that are happening here, and you're going to have 4. I've seen people do charts like this as well, where they put the 2 different events here and all the options along top and all the options down the side, and then they match them up like this, where heads and heads would make 1 there, heads and tails, tails and heads, where they intersect is what you write in the box, tails, tails. And you'll notice there's still 4 because 2 times 2 is 4. That works as well when it's this many. However, it becomes more complicated when you have more than just 2 independent events. So here's a question with this. What is the probability that 2 flipped coins will both be heads? Well, looking here, what's the only time that they were both heads? It was this first outcome, right? Those aren't both heads, those aren't both heads. So it is 1 out of these 4 options. So it would be 1 out of 4, which we can multiply by 25 and find out that it's 25 over 100, which equals 25%. Okay, what about both tails? Well, looking here, we have both tails was our last option. So it's just one of these options again, so it has to be the same. It's 25%. Part C, what's the possibility or the probability that 2 flip coins will be different sides flipped? So looking here, they're going to flip different sides. Heads are the same, tails are the same, whereas tails heads or heads tails are different. So there's 1 outcome here and 1 outcome here, which would be 1 plus 1 is 2 outcomes out of the 4, which 2 over 4 is 1/2, which we know is equal to 50%. So it's 50% likely that they'd be different. I'll do one more question here. Change my mind, I'm actually going to do 2, but here it says, what are the chances that they'd be either both heads or both tails? Now looking here, here's one option that are both heads. Here's an option that they're both tails, and it could be either this one or this one. That means that if it ends up this way or it ends up this way, you'd be correct. Let's say you're guessing the options. So there's 1 and there's 2 that would be it. So that again is 2 out of 4 chance, which is 50%. What about this question? Have at least 1 tails. So looking here, we've got no tails. So the first option doesn't work. The second outcome has 1 tails, so that works, so that's 1. This one has 1 tails, that works. And this one has 2, which is more than tails, which means that it is at least 1. There's at least 1 there, but there's another one. So this one works as well. So this would be a 3 out of 4 chance, which equals 75%. If the switching from fractions to percents is still an issue, please look back at, I believe it was the Unit 3 videos. There are also these things called spinners that are sometimes used for odds. You might have seen it on Wheel of Fortune, the game show. Basically, there's a certain amount of equal size sections, so it could be split into thirds, which means there's 3 different options, or into quarters, there's 4 different options. And there's this spinner that spins around. In Wheel of Fortune, they have it where it's like on the side and it like ticks around, and wherever that thing sticks would be the number that it is. These can be used, and all it means is there's 3 different outcomes, or there's 4 different outcomes. A die has 6 different outcomes. A coin has 2. So spinners are just something else that you might see in some of the questions. I'm going to do a complicated example here. Gregory flips a coin, then rolls a die, then spins a 3-section spinner, like this one up here. Heads is worth 6 points, tails is worth 2. The numbers on the spinner are 1, 2, and 6. And then the die, it's a standard die, so it's going to be 1, 2, 3, 4, 5, 6. So looking at this, how many different independent events are there? Well, there's the coin is 1, the die is 2, and the spinner is 3. So there's 3 independent events. So this tree diagram, the outcomes are going to have 3 different things in it. There's going to be 3 different columns for this tree diagram that we need to draw. The second part has to do with this sample space, is what it's called. That's when you write out all the outcomes in a list. And finally, how many outcomes will be over 13? We're going to have to use these last 2 sentences and switch the heads, tails, the numbers on the spinner, and add it up to figure out what would get over 13. So let's start off with the tree diagram. I've zoomed out here because I know that this question is pretty complex. How I know that is I know that there's 2 sides of a coin, I know there's 6 sides on a die, and I know there's 3 spinner sections, which means I know that the number of outcomes is going to be those 3 numbers multiplied. 2 times 6 is 12, times 3 for the sides of the spinner would be 36. So I need 36 lines eventually. So I've split this up a little bit here. So just looking here, I put my events, my 3 different events in columns in the order they happen. First, there's the coin, which a coin has 2 sides. It can be either heads or it could be tails. So I'm just going to put those there spread out. Then the die, I know that it could be 1, 2, 3, 4, 5, or 6, right? So I'm going to just write these down here. It could be 1, 2, 3, 4, 5, or 6. And then so that's there. I'm going to draw some lines. All right, so there's the 6 different options for my second event, rolling the die. It could be a 1, 2, 3, 4, 5, 6 after being a heads. But I also need to write those down here for all these other options. So it could be a 1, it could be a 2, it could be a 3, it could be a 4, it could be a 5, and it could be a 6 for being tails. I'll draw on my line. All right, now that I have my second event done, I need to remember that the spinner has 3 sides, correct? It has a 1, a 2, and a 3. So there's 3 different areas, 1, 2, or 6. I meant to say 6. Remember, it was a 6. So I'm going to write those down coming from each of these options. So this is going to look pretty complicated. I've got it going partially. All I do here is I write down 1, 2, 6, 1, 2, 6 over and over, and then I'm going to draw in the lines at the end. All right, there we have it. That's our tree diagram. We've got our 3 events, and we have, to start with, if there's 2 events, we just have 2 things that we write down. And then from each of those events, we have written down however many times this first event is. We write down our second event's options beside it, draw lines to it, the number of times that these events are. So there needs to be 6 twice because there were 2 events previous. We need 1, 2, 6 for our third event. We need to do that 12 times. Why? Because there were 6 here and 6 here. 6 plus 6 is 12, which means we need to write 1, 2, 6 12 times. And 12 times these 3 would be 36 different options or outcomes. So our outcomes here, we're going to write this down. All you do is you follow your line, and beside the last event, you'll write it down. So we could have an H11. So our outcome is going to be H11. Next one is H12. H12. Next is H16. Okay, we have those 3 H1s are done, right? Here, sometimes I find that it actually works easier to start from the end and go 1, 2, H, because this way I don't accidentally miss one going through. I just make sure I'm on the same line as the one that's the final event. So 2, 2, H, 2, 2, H, 6, 2, H, 6, 2, H. That looks like a 4. Another thing that I've done before is I realized that there's 3 that are going to start with H3, 3 are H4, 3 are H5. So I can do H3, 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 and do my 1, 2, 6. And I can do my H4, 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 go 1, 2, 6 again. Again, it's still those same 3 that are in a line together. I can do 1, H5, 2, H5, 6, H6, H6, H6. It's going to be 1, 2, 6. So your outcomes, you're just putting in all of the ones that show what path it is, what options they are. Okay, and then we're done with our H's. Half of them are going to be H's. Why? Because these are half of the options, and then the other half is tails. So half will start with heads, half will start with tails, because it's the equal likelihood. So what you could do as well is just write down tails over and over, because you know that that's what it's going to be. All of these are going to be tails, because all of them start with tails. And then you could write down 1 how many times? 1, 2, 3. So you could go 1, 1, 1, and the next number is 2, 3, 4, 5, and go 2, 3 times, 3, 3 times, 4, 4 times, sorry, 3 times, I'm going to say, 5, 3 times, and 6, 3 times. And then finally, just write down 1, 2, 6 over and over. 1, 2, 6, 1, 2, 6, 1, 2, 6, 1, 2, 6, 1, 2, 6, and 1, 2, 6. Again, I told you this was a pretty complicated one for this. So here's our tree diagram. This was part A of this question. We still have part B and part C. I'm not going to do part B fully. I'm just going to explain what it is. All you're going to do for part B is take these outcomes and write them out like you would like a sentence. You'll go H11, comma, H12, comma, H16, comma, H21, comma, H22, comma, and keep going until you get to the end. It's just listing them out in a row. Kind of like this list of numbers here, except you'll be putting your outcomes just like this on one of these older pages that I have, where you go number here, outcome here, outcome here, outcome here. Part C, it asked how many outcomes will be over 13. So if we remember in the question here, we were told that a heads was 6 and a tails was 2. And then the other ones we know it's 1, 2, 3, 4, 5, 6, and it's 1, 2, and 6. So if we think about it, these will be all added up. So it's going to be heads is 6 plus 1 plus 1. 1 plus 1 is 2 plus 6. This is going to be 8. 2 plus 1. Notice this just went up by 1, right? So this is 9. But then this goes up by 4 more, which would be 13. 6 plus 1 plus 6 is 13. And then we just keep working our way up. But as you notice, every time you do a group, all that's changing is that middle number, right? So every third one, you could just add 1 to, right? Because 1 plus 2 is 3 plus 6 is 9, which is just 1 more than this one up here. 2 plus 2 is 4 plus 6 is 10, which is just 1 more than 3 above it. 2 plus 6 is 8 plus 6 is 14, which is just 1 more than 1, 2, 3 above it. And we can just follow that pattern down until we get to the end of the heads, okay? So here I've finished filling these out, and just to check, 6 plus 6 plus h is 6 is 18. 3 times 6 is 18. So I didn't make a mistake there. We stopped halfway because tails, remember, tails is 2, right? Heads was 6. Tails is 2. So if you want, you could just copy these numbers down. And what's the difference between 6 and 2? It's 4 less, right? So it's going to be 4 less. If you think about it, 1 plus 2 is 4. 8 subtract 4 was 4, which means 9 subtract 4 would be 5. 13 subtract 4 would be 9. And we can keep doing that to the bottom. And just to check, 6 plus 6 is 12 plus tails is 2 is 14. And that's what I got following that through, that same pattern. Now that question asked how many outcomes will be over 13. So we need to go through all of these and count how many would be over 13. Notice it doesn't say over or equal to 13, it's over 13. that would suggest that 13 would not be included. It would just be the ones that are over 13. If it said 13 or more, would be 13 or more. It would be more than 13 or 13. 13 would be included, but this said over 13. So we need to only count the ones that are greater than 13. Going down here, we've got 1, 2, 3, 4, 5, 6, 7. So only 7 of these options here, 7 of these 36 options would be an outcome that's over 13. So would it be likely that that would happen? No, that wouldn't be very likely. Let's do a little math. 7 over 36. We need to divide that. Did some double-digit division, long division here, and found that I had this repeating number start happening here. The odds of this happening, the probability of this happening would be a 19.4 repeated percent. So approximately, just approximately 19% likely. So, which is pretty close to 20%. It would be a 1 in 5 chance approximately that this would happen. So, which is more likely? It's far more likely that you would get a number that's 13 or less. If you were playing some game with this, or Gregory was just trying to have some fun with probability here. I want to repeat that this question here is a pretty difficult one. This is more difficult than you'd probably see on a quiz or an exam. But it's pretty neat how many options that there can be. And you're going to notice in here that there's some options that repeat. Like, what are the chances that it would be a 13? Count. There's 1, 2, 3, 4. There's 4 different ones. So 4 out of 36. So even less likely that it'd be exactly a 13. So I hope this helps see why tree diagrams can be useful. They take a little while to do, but they're a really good way to see all of the different options. Which is the most common option would be another question that might be asked. You'd have to count up how many of each of the numbers there are. It could be 8 possibly is my thoughts of what the most common one is, because both sets have 8s in it. There's 2 here, and then there's oh no, it's just 1, maybe 11. Who knows? I do. It was 3 options are 11. I'll stop rambling. I think this is the longest video we've had yet.